A radar system fielded in 1959 can detect an F-35 more reliably than radars built 50 years later. This is not a flaw in the old technology. It is a consequence of physics that hundreds of billions in stealth investment were never designed to defeat. But detection of a stealth aircraft and guiding a missile to it are two entirely different problems. The space between them is where this story begins. After World War II, radar engineers in the Soviet Union and the West faced a fundamental choice: pursue greater detection range or sharper resolution. The Soviets, anticipating high-altitude threats from American bombers and reconnaissance aircraft, committed to early warning systems operating in the VHF band. The P-14 Tall King, introduced in 1959, embodied this approach. Towering nearly 50 meters, it swept the horizon with meter-long radio waves reaching hundreds of kilometers beyond the radar horizon. Western observers often dismissed these VHF systems as outdated, but Soviet doctrines saw their value. Long wavelengths could penetrate atmospheric clutter and, crucially, interact with aircraft in ways that higher frequencies could not. As stealth technology began to emerge, the Soviets recognized that VHF waves were less easily fooled by shaping and coatings designed to scatter or absorb radar energy. By the mid-1960s, NATO and the US Air Force had charted a different course. Procurement records and doctrinal papers from this era show a clear preference for S-band and X-band radars. Systems like ANFPS-20 and ANFPS-79 offered much finer resolution, tracking fast, low-flying targets with precision. The logic was straightforward. Shorter wavelengths meant more detail, allowing interceptors and missile batteries to lock onto targets quickly and reliably. In a world where seconds mattered, this precision was prized above all else. Yet as Western radars climbed the frequency spectrum, they sacrificed the raw reach of VHF. High-frequency systems excelled at tracking, but their signals reflected weakly from stealthy shapes. Soviet VHF radars like the P-14, though less precise, could still detect the presence of aircraft designed to evade detection at higher frequencies. This information was often too coarse for direct targeting. Fire control still required higher frequency radars, but early warning was preserved. The P-14 remains a testament to this divergence. Rather than obsolete, it stands as a relic of an era shaped by competing assumptions about what mattered most: seeing farther or seeing finer. Radar's effectiveness depends on the relationship between its wavelength and the size of what it's searching for. VHF radars from the 1960s, such as the Soviet P-14 and P-18, operate with wavelengths between 1 and 3 meters, roughly the length of a compact car. By contrast, modern air defense radars often use X-band or S-band, with wavelengths around 3 centimeters, about the width of a finger. This difference shapes how radar waves interact with aircraft, and it is why stealth technology is not foolproof. Stealth aircraft rely on flat panels and sharp angles to scatter radar waves, a method that works best when the radar's wavelength is much smaller than the aircraft's features. At X-band, centimeter scale waves bounce off these surfaces like light off a mirror. The F-117, for example, was built with hundreds of angled facets, each about 1 to 2 meters across, to confuse these shorter waves. But when radar wavelengths stretch to 1 or 2 meters, as in VHF, the rules change. Now the size of the aircraft's edges and panels can match the radar's wavelength, causing resonance. Instead of deflecting energy, these features act like antennas, re-radiating energy back to the radar. This resonance regime produces a spike in radar cross-section, as seen in studies of the F-117 around 100 MHz, and similar effects in the F-22 and F-35, where tail edges and engine inlets reflect strongly at certain VHF frequencies. Radar absorbent material offers another layer of stealth, but its effectiveness depends on skin depth, the distance a wave penetrates before being absorbed. At X-band, a thin radar absorbent layer works. At VHF, skin depth can reach several centimeters, far thicker than practical coatings. The radar wave passes through, reflecting off the metal beneath. VHF radars can detect stealth aircraft when geometry and frequency align, but their long wavelength limits precision. They can reveal something unusual in the sky, but pinpointing exact coordinates requires higher frequency radars, which stealth shaping and radar absorbent material are designed to defeat. On March 27, 1999, just after nightfall, the Yugoslav 250th Air Defense Missile Brigade prepared for another round of NATO airstrikes. The commander, a veteran of the old Soviet radar school, ordered his crew to wait in silence, listening for faint signals among the noise. At 20:38 UTC, the P-18 VHF radar, callsign Sokol-1, picked up an unusual return, something moving low about 55 kilometers away. The crew had seen these faint blips before, but this time the commander decided to act. He directed the radar operator to switch from passive listening to active search, but only for a brief window. The P-18's transmitter was energized for just 17 seconds, enough to cue the SA-3 Never Fire Control radar without drawing NATO's anti-radiation missiles. Within seconds, the SA-3's narrow beam locked onto the coordinates provided by the P-18. At 20:39 UTC, a missile streaked into the night sky. 2 minutes later, the F-117 broke apart over Serbian farmland. The pilot, Lieutenant Colonel Daryl Zelko, ejected and survived, later rescued by NATO forces. The engagement was over almost as quickly as it began. The P-18 had revealed the stealth aircraft's presence, but the missile could only be guided once the higher frequency fire control radar took over. This sequence, detection by meter-band radar, rapid handoff, and a tightly controlled emission window, demonstrated how physics and disciplined tactics could pierce the aura of stealth. But even in success, the system's limits were clear. VHF could find but not target. Only a coordinated network could finish the job. Meter-band radars like the P-14 and P-18 offer a unique window into the sky, but their strengths come with hard limits. The first and most visible is size. To focus long wavelength signals, these systems require antennas stretching tens of meters. The P-14's array, for instance, spans nearly 50 meters, larger than a tennis court. This scale is not just a logistical burden, it also shapes what the radar can and cannot do. The beam it forms is broad, sometimes several degrees wide, which means that while the radar can alert operators to a distant object, it cannot pinpoint its location with the precision needed for a missile shot. This coarse resolution forces air defense crews to rely on higher frequency radars for targeting. The handoff between detection and engagement is not seamless. Each switch introduces delay and risk. Meanwhile, the sheer size of VHF antennas makes them hard to conceal. Once active, their emissions are easy prey for anti-radiation missiles like the AGM-88 HARM. Crews must limit transmission time, often to seconds, to avoid being targeted themselves. In practical terms, detecting a stealth aircraft at long range is only the first step. Without a narrower beam and sharper resolution, the VHF radar cannot guide a missile to its mark. The promise of early warning remains real, but the challenge of turning that warning into a successful intercept remains unsolved by meter-band systems alone. Across Russia, China, and Iran, a new generation of meter-band radars is coming online. The Russian Nebo-M system, first fielded in 2013, combines VHF L-band and X-band arrays on a single platform. Its VHF component stretches over 10 meters, designed to catch the faint echoes of low, observable aircraft at long range. China's JY-27A, unveiled in 2015, also operates in the meter band and is reported to track targets hundreds of kilometers away. Iran claims its Qadir radar can detect stealth aircraft at 1,100 kilometers, though independent verification is scarce. These systems do not replace high-frequency radars but work alongside them, providing early warning and cueing for more precise fire control sensors. The renewed investment in meter-band technology reflects a global recognition. While modern stealth can defeat most radars, it cannot erase the physics of resonance and wavelength. The search for truly undetectable aircraft has become a contest of spectrum, not just shapes and coatings. In recent years, the public rollout of the B-21 radar has offered a rare glimpse into how stealth design is evolving in response to the low-frequency radar threat. Official statements from the program have directly acknowledged the challenge posed by very high-frequency and ultra-high-frequency radars, an admission that stands out in the world of military aviation, where specifics about vulnerabilities are rarely discussed. The B-21's designers have referenced the need to account for detection by long wavelength systems, hinting at changes in shaping, materials, and operational concepts. This feedback loop, where advances in radar prompt new approaches in stealth, and vice versa, drives the ongoing contest between aircraft and air defense engineers. The fact that the United States Air Force now openly considers meter-band radars a credible risk underscores how lessons from decades-old technology continue to shape the next generation of so-called invisible aircraft. Today, VHF radars can spot what stealth was meant to hide, but spotting is not targeting. Without precise fire control, detection alone cannot close the kill chain. As new air defense networks fuse old wavelengths with modern tracking, the race is not just about hiding or seeing, it is about outthinking the physics.